Here's how to use conservation of energy in physics. So in this example, we have an 80-kilogram roller coaster that starts at point A, with a height of 200 meters and a speed of 20 meters per second. We're then asked to figure out how fast the roller coaster is moving when it reaches the bottom, point B, and how fast it is moving when it goes back up to point C at a height of 160 meters. The key to solving these types of problems is to calculate the total energy at one point, where both the speed and height are known, and then set that equal to the total energy at another point, where either the speed or height is unknown. For simple problems like this, there are just two types of energy, kinetic and potential. In later examples, we'll add more types of energy, such as rotational, friction, and springs. But for now, kinetic energy can be thought of as the energy related to how fast something is moving. And potential energy is related to its height. It turns out that as our roller coaster travels from point A to point C, it will trade off how much energy is in kinetic and how much is in potential. But by the conservation of energy, the total energy will always remain the same. The first thing we're going to do is calculate the kinetic energy at point A, which is equal to 1/2 times the mass times the velocity squared. Next, we're going to calculate the potential energy, which is equal to the mass times gravity times the height. Quick note. When putting in a number for the height, you can technically measure it from any spot, as long as you are consistent and measure it from the same spot at both point A and point B. In this case, we're going to measure the height from the ground and call that 0. But you may see other problems where the height is measured from somewhere in the air, and thus height can be negative. So moving on, we now add the kinetic and potential energy together to get the total energy at point A, which is 173,000 joules. Looking at point B, we're asked to find the velocity, which we will figure out by writing out the equations for the kinetic and potential energy. Here, kinetic is again 1/2 mv squared, where v is unknown, so we'll just leave it as a variable. And the potential is mgh, but since the roller coaster is on the ground, h equals 0, so the whole potential is 0. This shows how all the potential energy has transferred into kinetic energy, and so the total energy at point B is just equal to 1/2 mv squared. Now by the conservation of energy, this total energy at point B must also equal the 173,000 joules of total energy at point A. So all that's left to do is to solve for v, which gives us a speed of 65.8 meters per second. Now looking at point C, when the roller coaster has regained some height, this means that some of the kinetic energy will shift back to potential energy. Writing out our expressions for kinetic and potential energy, we will add them together and again set them equal to the total energy at point A. All that's left to do now is a little algebra, and you'll see that the velocity at point C is 34.5 meters per second. And there you have it. That's how to use conservation of energy in physics.